Today we're gonna study the magnetic force on a current wire. Magnetic force on a current wire. Let's see, for example, we have some wire. Here is a wire with some current going to the right. Let's call this current I1, okay? And let's see, this wire has certain length. We call that length L. So this is the length of the wire, L. Now, what happened is we put this current in a magnetic field. And the magnetic field, let's see, is going onto the paper. So we look at here the back of the arrow. So we put this cross, it means this is the back of the arrow. And the arrow is going onto the paper, which means the magnetic field is going onto the paper. So the B field is going like that onto the paper. And this B field doesn't belong to the wire. This B field is coming from somewhere else. It could be coming from another wire or from a magnet or from the earth. Some magnetic field, an outsider. Now, this wire will experience a force. And that force, we'll write it here. F is equal to I1 L cross B. This is the force. Now, why will this wire experience a force? The reason this wire experiences a force, because this wire itself has its own magnetic field. Okay? And that magnetic field of this wire will interact with the magnetic field of the outside. Let's see, for example, we need to know the direction of the magnetic field of this wire. So we do the thumb rule. We grab the wire with our right hand like this. Here is the wire. Let's see, the wire is the pen. And then I grab the pen and look at my thumb is going to the right. It's in the direction of the current. And if you look at my fingers, they're coming up at the top here. So I put here some circle. This is coming from the paper. So we call this one B1, the magnetic field B1 of this I1. And then if we keep turning our fingers, turn it all the way down to this location here. At that location, you can see my fingers are going onto the paper. So we put here the back of the arrow, and then we put B1. So this B1 is the magnetic field of the wire. It belongs to the wire. It's coming due to the current in the wire. Now this magnetic field B1 interacts with this B field. That's why there is this force. We have interaction of two fields. Now here in this force, we have to put the B field B, not B1, because this B is an outside B field where we put the current in it. Now we need to know the direction of this force, which way the wire is gonna feel the force. Now, what you do, you use the right hand rule. So you can see I'm sitting this way. So what I'm gonna do, I'm gonna turn the paper so I don't have to turn around. So I go like this, turn the paper like that. Can you see now here? And then I use my right hand. So the current is going up like that. So my fingers, they're gonna go up with the current. You see, I have that L. L is the length of the wire. L will follow the direction of the current. So, but B is going onto the paper. So I rotate, the palm of my hand needs to be going in the direction of the B field. And then I rotate my fingers towards the B field and look at my thumb. My thumb is pointing up. So the force acting on the wire is going up like that. That's the force. So now we know the direction of the force. Now you can see the B field and L. The B field is going into the paper and L is going like that, horizontally. So they're perpendicular. So I don't have that sine theta that comes from the cross product. So I just put here F is equal to I1 LB. And this is the force acting on the wire, on that wire with current I1. Now what's so interesting about this wire, you can put some object on the wire. You see, if this wire is connected to some wall or some object here or some like stand like this, like that stand, then the wire will try to go up, but it can't because it's fixed at these 2 points. Let's see, point A and point B. It's fixed at those 2 points. So the wire will go something like this, like that. So if you take this wire and then you put something on top of it, this thing doesn't have to be a wire. It can be a rod. This can be a rod like this, and the current is going, the current I1 is going through the rod. And then here we have some mass. This mass has some weight, we call it mg. Now remember, we put the magnetic field from outside is going in, so the force is gonna go up. So you can actually lift something with this rod. If we apply Newton's law, we say ma, let's choose the acceleration going up, for example. This is just to write down our equation. So we put ma is equal to F minus mg. Now let's see, this wire or this bar is not going up, is we try to find the current that we have. This force F here is equal to the weight. We need to find the current that's going to give us this equality. So what we do, we put A is equal to 0 because the wire is not moving. And then we have F is equal to mg. Now, as you see, we calculated this F, it's here. So I can put I1 LB is equal to mg. Now the current I is equal to mg over LB. And you can see here that you can put some mass like 10 kilograms, 1,000 kilograms. So it depends on the magnetic field. So this current here, if the current is so high, then it will kind of make lift this object. It will lift it. Okay. Now, if you look at here, if the mass, we can switch the equation. We can make it look like this. We can put here B is equal to mg over I1L. This is also an equation. So you can see, if you want to increase the mass, you have to increase the B field, this outside B field. If you want to increase the mass, to lift some heavy mass, you need to increase the current. So now we know the magnetic force on the current wire. Okay? See you.